Okay, so today we are just going to have 15 minutes of online learning because tutorial will only start on week 3. Okay, so I believe everyone has a copy of this PDF notes, which is available in Spectrum. Okay, and on Tuesday, I think we covered up to the history, right? Okay, talk about the Monty Hall problem and why we cannot rely on just intuition to study probability because it can mislead quite easily. Okay, so and then some history. So I think you can read the examples on your own. Okay, that's just for motivation purpose, right? So for today, I want to cover some background material on the mathematical preliminaries. Okay, we are going to cover until. So I'm going to go through the material with you until theorem 3.2.1. Okay, and then the rest of the material you can read it first, and then we will go through them on next Tuesday. All right. Okay. So it's good if you have some paper and a pen with you so that you can try out things as we go on, right? Okay, ready, everyone? Okay, I'm just going to turn to the whiteboard so that I can write something, and you can refer to the notes separately, okay? So let me look at the whiteboard. Okay, so so let's talk about some basic things in analysis, which is, so I'm going to go, I'm talking about definition 3.1.1 now, the supremum of a set, right, of real numbers, okay? So basically, this is actually quite easy. So we're going to look at some examples. So the example that I gave you there was a set, right? So this is the set of numbers from, so on the real line, you have from 0 until 1, right? So this is actually a closed set, right? So this denotes closure. Okay, of course, just to refresh, if you can open the set, right? If you open the set like this, that means you would actually represent it like this. Okay, meaning that these two endpoints are not included. Yeah, so this is just some revision. Okay, and of course, if you have this closed set 0 to 1, we can first talk about its upper bound, right? Okay, so upper bound is some value that this any element in this set, right? I can say that let's say x is, so a is some element in E, right? So it could be any element inside this interval. So if you have an upper bound, it's actually any value where your element in E cannot exceed, right? At most it is equal to it. So very clearly here, we know that 1 is an upper bound, right? Okay, upper bound for E, it can be 1. Okay, it can be 1.1. It can be 2. It can be a whole lot of other things, right? Like for example, it can be any value that is going on, that is towards the right hand side of this interval is an upper bound for E. All right. Okay, because the elements in in E cannot exceed these values, right? And then we want to, when we talk about the supremum of E, we are basically saying the smallest among all possible upper bounds. Smallest among all possible upper bounds, okay? So clearly the supremum here is actually this value, right? Okay, it's this value, right? Because this is among all the upper bounds that are possible for this set, this one is the smallest one, okay? So we call it the supremum of E. Right, is that clear?
Yes, Doctor, very clear.
Okay, just as some other example. So suppose I have a set E equals to something like this. Union So what is supremum of E? This U here means the union, right? So this is a set operation, okay? So can you see clearly what is the supremum of E here? Someone can just shout out the answer, or you can also type. So remember, the supremum of E, right, is the value whereby all elements in this set, right, they cannot exceed this value. And this is the smallest among all possible upper bounds for E. What would that be? Anyone wants to try?
Is it 7?
Okay, so, okay, 7. Sutta also says it's 7. All right? Do you agree it's 7? Can everyone else see that it's 7? So basically, it's actually quite straightforward. It is 7. Because this set, right, is basically if you have a real line here, so it includes from -1, so this is 0, so this is maybe 2, and here is 5 until 7, right? So this set E, right, consists of all the numbers in this interval, okay? So therefore, if you use, so therefore, following the definition, right, so you can think of upper bounds for E. So clearly the upper bound cannot be in this interval, right? Because then it would be actually smaller than this value, right? Because you have to see that E consists of 2 parts, okay? So and clearly the upper bound cannot lie over here, and it can also cannot lie over here. So therefore it has to lie all over here, right? All the upper bounds, okay? And there are of course many upper bounds. There could be like 8, 9, or whatever, 100. Those are all upper bounds, right? But when we want to find supremum, we want to find the smallest amount upper bound, right? So it turns out that it is 7. Okay? Yeah, that's clear to everyone, right? It's actually not a very difficult concept, okay? And after that, so I want to maybe explain the small difference between supremum of a set and the maximum of a set. Okay. Sometimes they are the same, but sometimes, in general, they are not the same. Although in certain situations they can be the same. For example, in this case, the supremum of E, I better write it like this, is actually equal to the max of this interval, which is 1. Okay, you have to notice that max, right? Max and sup are slightly different because for max, that particular value has to be inside, right? So when you talk about max, right, this value has to be inside this interval. Okay. Whereas although you have sup of, if you have a closed, if your right end is not closed, your sup is still 1, but you don't have a max, right? Does not exist. Okay. Is it clear to everyone why the max does not exist for this open interval? Is it 1? Can you say that it is 1? Can we say that the max of the this interval where the right side is open is equal to 1? Yeah, so we can't say that, right? Because 1 is not inside this set, right? Yeah, because you notice this, this is open, so 1 is actually not inside, all right? So in mathematics, when we say things, we are very precise. Yeah, it's not like fuzzy kind of things. Okay, it doesn't exist because, okay, so maybe you can say that 0.999 is large, but you can always find another number that is larger than this. Like for example, 0.999, and then you can keep on adding 9s, right? It doesn't end, right? And as long as you add 1 digit to the decimal place here, you can always find some number that is larger than the previous one. Okay, so it just keeps on going, and therefore there's actually no. When you say that there's a max, right? There's only one candidate. There's only is the solution is unique. Yeah. So over here, you can keep on adding decimals, and it just doesn't end. Okay, so in this case, we don't have a max, right? Although we would have a sup. Okay, so a sup is actually more useful in some sense to overcome the situation of max, because sometimes you want to use max as some kind of a bound, right? But for the set that you're working on, you'll find that will be a problem because your endpoint is actually not closed. Okay, so is that clear for everyone? So for the definition, you can, the definition is kind of like just a bit more formal way of explaining things, okay? So I leave it to you to read it, okay? I just explain the ideas with examples. Right, is that okay for everyone? Okay, so I'm going to clear the board now. Okay, so if you can have supremum, sup is the supremum. We also have something that is the reverse, okay, something like the reverse, which is something called infimum of a set, right? So just now we used the example of okay, this interval, and we know that sup E is 1. So in this case, the infimum of E is 0, okay? So basically, it works similar like the sup, except that is going on the left side. So you have, let's say, 0 here, 1 here. This is an interval, right? Okay. So of course, this is talking about the lower bounds. So you can find lower bounds for this set. Of course, the lower bounds will all be here, right? So there will be all the values that are smaller than the smallest member in E. And of course, what are the possible lower bounds? -1, -2, -3, -1.5, whatever, okay? Any value on this side, they can be a lower bound, right? But then we want to find out the largest among the lower bounds. Okay, and it turns out that the largest would be actually 0, right? Because 0 is actually a lower bound, right? Because your elements here, right, are not, they are at least as large as 0. Okay, so 0 is actually a lower bound for E, and among these guys, 0 is the one that is on the rightmost. Okay, so that's why we have infimum of E is equal to 0. Okay, and in this case, your infimum of E is actually also equal to the minimum of E. All right, and if you have the open set 0, 1 like this, okay, so this is your 0, this is your 1. Your infimum of E will still be 0, but then the minimum of E does not exist. Okay, for the same reason that I explained just now for the sup and the max, right? Because 0 here is not an 0. It's not a minimum because you can always find some value that is arbitrarily close to 0, right? Since 0 is actually not inside this interval. Okay. So so we have just come across the concept of sup of a set and the infimum of a set. Okay. Is that clear to everyone? Okay, right, good. I think this is actually quite simple. And then I just briefly talk about the theorem 3.1.1, the approximation property for suprema. So basically, it's just saying that if you have some set E, right, with some interval, okay. So the supremum of, it says that the supremum of E, right, if you have some element that is inside, so A is some element in E, right? So this element is definitely bounded from above by sup E, right? Because your sup E will be here. So your A cannot actually escape sup E, right? I think everybody agrees with this. This is very obvious. And then now, then it says that it is larger than sup E minus some epsilon. Okay, which is basically saying that so sup E minus some epsilon will be some, so you start from here and then you go backwards up to an amount epsilon, right? So you would get, like for example, you will get something like here, right? So this will be your sup E minus epsilon, right? Okay, it's saying that so you might, this might be your A here, right? It's saying that for any A that you have, right, you can always find some epsilon, okay, so that the A is trapped between sub E minus epsilon. All right, it's just simple. It's just like you're trying to catch your A, right? You're trying to imprison your A between sub E and some other deviation from sub E, okay, by a certain amount. And you can always find that regardless of what A is, as long as your A is inside this interval. For example, if your A is here, right, then your epsilon will go somewhere around here, okay? Subtract, so your sub E minus epsilon will be sitting here. So your A will be trapped between here and here, right? So this epsilon will depend on what element A is, okay? It just says, the theorem just asserts that you can always find something like this, all right? Okay? And then there's an axiom called the completeness axiom, right? Which simply says that if E is a non-empty subset of the set of real numbers that is bounded above, then E has a supremum. Okay, this is obvious. Okay, if it's bounded above, then it has a supremum. Okay, because you can always find the smallest among the lower bounds. All right. And then go to theorem 3.1.2, the density of rationales. This result is basically saying that just to check with everyone, does everyone know what rational numbers are? Usually, you would denote this with the set of rational numbers will be denoted using Q. Yeah. R is for the set of real numbers. Okay. So Q will denote the set of rational numbers. So what are rational numbers? Anyone wants to just shout out?
It's when you can divide two integers, like a decimal.
Okay, so basically it's just the ratio of two integers, right? Two integers. For example, you can have some value like A over B, where A is integer, is a positive integer, and B is also a positive integer, right? Okay, so for example, 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on are rational numbers. 2 over 1, 2 over 2, 2 over 3, and so on, right? So these are called rational numbers, okay? Very simple. Theorem 3.1.2 just asserts that you can always find two real numbers that will imprison any rational number that you can find. And this seems very intuitive. Okay, that's why, although you can prove it, but there's just too many proofs, so we can't go through all of them. So any of these theorems that are actually quite obvious, we'll just take it as a result, yeah? So it's just saying that any of these rational numbers, you can find two real numbers to imprison them, for sure. It's very obvious. Like for example, this rational number, you can obviously imprison it using 0 and like 1.1, right? And for this one, you can imprison it with maybe, let's say, 1 over 2, you add a small number, epsilon, and 1 over 2, you subtract some small number, epsilon. This epsilon can be just anything. So one strategy to actually imprison your rationale is that you just take the rationale itself, and then you add to the right-hand side, you add some small number or a large number, doesn't matter, any arbitrary number. And to the left, you subtract equal amounts. Okay, then you can find some bounds for it. Okay. All right. Is that clear? Okay. All right. So then definition 3.1.3, you have boundedness of a set. It is just to define what we mean by bounded, right? Bounded means if and only if it's bounded below and above. Okay. That means you can find two values such that it's imprisoned, okay, by those two numbers. Let me clear this drawing. So for example, some set like this is bounded, right? Because it's bounded from below and above, right? You can see this because sub E is 5 and infimum of E is 0. Okay, but but then the set is unbounded. Okay, because it's not bounded below. Okay, you see that it goes all the way to infinity, right? So there is actually no bound below. Okay, please take note that infinity is a concept, right? It's not a number, yeah. Okay, so generally we will not you cannot do any algebra on infinity because it's actually not a number. It just means some number that is extremely large. Okay, for example, you can't say that you can't say that this is larger than this, right? Although it's tempting, but you can't because this is actually, when you want to apply an arithmetic operation, this has to be some integer, right? So this infinity here just represents a concept. It doesn't represent any integer, okay? So you can't have things like this, all right? So it's just a concept, okay? And then just going through theorem 3.1.3, there are two assertions there, which you can actually check easily. It says that E has a supremum if and only if minus E has infimum. And then infimum of minus E is equal to minus sup of E. Okay, you can actually look at some examples, like for example, if you have E equals to something like this, then E has a supremum, right? Clearly it has a supremum, right? So if and only if this has an infimum, and this is true. And you can actually check this very easily, okay? So minus E, you will get minus 2, 1, right? Agree? You just multiply minus 1 to this set, so it will flip, right? Your right end and the left end will flip. And the infimum of minus E is clearly minus 2, which is equal to minus supremum E, right? Because sub E is 2, right? Okay, so this relationship actually holds. All right. And then for statement 2, I'll leave it to verify it yourself. Yeah. Okay. E has an infimum if and only if minus E has a supremum. In which case you have that relationship, right? And then you have the monotone property. If you have
Sir? Hello, sir?
yes.
So basically, for all sets that are unbounded, there's no infimum and no supremum.
Yeah. So if it's the infimum and supremum, they are bounds. Yeah. If it's unbounded, there's no. Then if it's infinity, there's no bound.
Yeah, so basically the second set that goes from minus infinity to 1, we can't say that 1 is a supremum because the whole set is
You can. Yes, you can. It's just that it doesn't have an infimum.
Oh, so we can, like a set can have a supremum, but sometimes not an infimum, and vice versa.
Yeah, that's right. I mean, like if you look at it carefully, it says unbounded, right? Unbounded means it has to have upper and lower bound together.
Yeah.
Yeah, in this case, yeah, it still has an upper bound, right?
Yes.
So you can say that sub e here, in this case, sub e is 1, but infimum of e does not exist, okay?
Okay, all right, thank you.
All right. So theorem 3.1.4 basically is just saying that it's just giving some kind of comparison between the supremum of infimum of two sets, whereby one of the set is a subset of the other. Okay, so let me clear this. So for example, if you have A being a subset of B, which basically like saying that you may have something like this is your set A, this is your set B, right? B is the whole thing. A is nested in B. Then of course the supremum of A cannot exceed the supremum of B, right? At most they are the same. That's when A is actually equal to B, right? Actually, it need not actually be equal to B. You can still have that. For example, let's say you have A equals to some set. Please remember that the set need not always be an interval. Yeah, it can be consisting of numbers like this. And let's say your B is maybe an interval from 0 to 10, right? Okay, so clearly here A is a subset of B, right? Agree? Because your B is running from 0 to 10, and this is your B, right? And your A it consists of the collection of values which is 1, 5, and 10. Okay, so definitely your A is inside B, all right? And in this case, your sub A is actually equal to 10, right? And sub B also equal to 10. Okay, so in this case, although your A is much smaller than your B, but they both have the same supremum because it turns out that this actually depends on the right hand endpoint. Okay, right. So this is actually quite intuitive. It says that then if B has an infimum, then the infimum of A has to be larger than or equal to B. Now in this case, right, using the same example, infimum of A is equal to 1, right? And infimum of B is equal to 0, right? So infimum of A is definitely larger than infimum of B. Okay. So your infimum is the largest among the lower bounds, right? Since your A is inside B, so its left end, right, will be generally equal to the left end of the larger set or towards the right of the larger set. Okay, so this actually holds. All right. Okay. So this is just very quite simple material. It's just to establish bounds. Yeah. In this course, we will use a lot of ideas about bounds. Yeah. Maybe you have maybe you have to get familiar with this idea of thinking. In a lot of cases, we don't need to make exact calculations. Okay, I know that you might think that, oh, you always have a formula or whatever. That sometimes it's not necessary, right? Sometimes we just need to work with bounds, because sometimes getting exact formula is actually very difficult, right? And we don't actually need to, because if you're working with limits, right, your limiting processes, you just want to see what will happen to the bound, okay, not the exact formula, right? So here you will, that's why in this course you will keep seeing a lot of these inequalities coming out, whereby we focus on establishing bounds, and then we observe what is the behavior of these bounds when we have a limiting process. Okay. All right, okay. So we have about 10 minutes more, so I'm just going to talk about maybe just one more thing, countability of sets. Okay, countability of sets, right? If you look at definition 3.2.1, right, there are 4 points there. The first point is finiteness. Okay, it says that E is finite if and only if your E is the empty set. Okay, the empty set, or you can actually find some kind of a one-to-one mapping from the set of natural numbers to E. Okay, for example, suppose your set E is 1, 2, 5, 7, right? It's 4 values, okay? So this is a set of natural numbers. Okay, if you can find a one-to-one mapping from the set of natural numbers to E, then you have you can find a one-to-one mapping, yeah? So then you can say that E is finite. For example, 1 maps to 1, 2 maps to 2, 3 maps to 5, 4 maps to 7. That's done already, right? You use the 4 numbers in the set of natural numbers to map to all the members in E, right? So you have a one-to-one mapping. And therefore, you say that E is finite. Okay? But most people, I guess, would just approach finiteness as a kind of intuition, right? Like if you have something that you can, if you can actually count the number of elements in some set, then you say that it's finite, okay? That's based on an intuitive notion. And of course, if you want to make the notion to be watertight, then you have to use this idea of one-to-one mapping, okay? So you can see the difference between intuitive thinking and kind of like a more rigorous way of defining things in mathematics. Then number 2, we say that the E is countable. Now this is a word that has some important meaning, right? Countable. If and only if there is a one-to-one function from N to E. Okay. Now, countability is basically just defined as such, right? As long as you can find some one-to-one function from the set of natural numbers to E, then we say that the set is countable. Okay. The simplest example, so it doesn't matter. Your E can actually be infinite. It can be infinitely large, and yet be countable. Okay, I'll give you an example. So if you just have E as 1, 2, 3, 4 until all the way, it doesn't end, right? Okay, so you just have 1, 2, 3, 4, 5 all the way until infinity. It just doesn't end, right? This set is countable because you can have a one-to-one mapping with the numbers in the set of real sorry, the set of integers, right? It's very simple. In this case, one just, so you have, you have one from the set of natural numbers. One maps to one, two maps to two, three maps to three, four maps to four, right? So this is very easy, okay? So you can see that it doesn't end, right? The mapping will just go on. Okay. Let me clear the whiteboard a bit. How about this set? Maybe I'll just draw it. Oops. Clear this. Okay. Maybe I'll just draw it like this. How about if you have a set that is like this? 0, 1, 2, 3, 4, 5, and so on. And you have the set of natural numbers here. 1, 2, 3, 4, 5, 6, and so on. Okay. Can somebody tell me how you would actually establish a one-to-one mapping from N to E so that you can show that E is actually countable? Any ideas?
X minus 1.
Sorry? Just find, just mention how you would actually map the numbers from N to E. That's one by one, and then you will have that every number in E here will have a partner from N. You just want, you can actually solve this by a verbal description. Anybody wants to just give that? Is it clear enough in this case? How you would approach the problem? No, is there some response from the student?
If it's X plus 1 and X belong to the set E, using function.
Okay, you just need to think of it as a mapping, right? So like for example, one example here would be if you map 1 to a number that is 1 less to it. So your rule is map, if you have N as an element in N, the rule is you map N to a number in E that is 1 less than it. Okay, so 1 will map to 0, 2 maps to 1, 3 map to 2, and so on, right? So then you have a one-to-one mapping, and therefore E is countable. Okay. in this example is actually quite easy. But what about this set? Let me clear this. So the set of clear this. So if your set is the set of integers like this. Now, how would you show that E is countable? How should you do the mapping? How? So your set of natural numbers is 1, 2, 3, 4, 5. How do you establish a one-to-one mapping here? So these are the elements in the set E, right? How do you do the one-to-one mapping? Any suggestions how you would proceed? As long as you can find a partner. So the mapping here is basically just saying that find a partner in for all the elements in the set of natural numbers n with E, yeah? As long as you can find some rule that assigns a partner from n to E, you are done already. Okay? So depending on what E is, your rule will have to adjust slightly, but then as long as you can show some way to a rule to partner numbers in n to E, you are done already with showing countability. Because later we are going to explain that the set of rational numbers is countable. Okay, that has a very interesting way of mapping n to the set of Q. Anyone wants to give it a try here? We are about to end now.
Maybe map element in N to the element in E that is less 6.
That is what?
Less 6.
Less 6. But yeah, but okay, this is just an illustration. Maybe you are, I made you think that it doesn't end. Yeah, it just it doesn't end because these two are infinite sets.
Doctor, maybe every element in N goes to its negative partner in E or positive partner in E.
Okay, If you do it like that, then it will be very puzzling. Okay, so if 1 comes here, 2 comes here, 3 comes here, 4 comes here, right? Then how about here? How do you map? If you take the natural numbers, okay, 1 to 1, 2 to 2, 3 to 3, 4 to 4, and you partner like this, right? You keep on partnering, so these guys got no partners, right? So, and that would be very hard to argue countability. Or if you partner to the negative side, also is a little bit difficult, right? Like for example, if you partner like this, 1, 2, 3, 4. Sorry, this is actually 4, right? You partner like this also a bit hard because then it would seem like this part has no partners, right? So any ideas? Do it in a way that you are sure that if you continue doing that, everyone will have a partner. That means it's kind of like you are drawing some kind of line. You kind of like moving, starting from somewhere here, and you're moving through this, and you are sure that you are covering both sides equally. Now, how would you do that? No, in this case, we don't have absolute functions because you have to treat them as they are and find some rule to move through this place. Okay, maybe something like this. Okay, let me show you a suggestion. So for 1, you start with 1. Okay, you start 1 here. Then for 2, so this is over here, this is N, yeah? Over here, this is E, right? So 1, you map with 1, okay? Then for 2, you come here. Okay? For 3, you go here. Right? 1 is matching with 1, 2 will match with 0, 3 will match with 2, for 4, you go here. For 5, you go here. For 6, you go the other side. Then for 7, you go there, right? You are swinging, right? You are swinging from left to right, to left to right, to left to right. So can you see that if you do it in that way, you are going to cover? So for example, like my function will be 1. So this is from N, right? So okay. So my function will be F1 to 1, F2 to 0, F3 to 2, F4 to -1, F5 to 3, F6 to -2, and so on, right? That means so my rule is I'll take 1. So you can see that all these numbers are 1, 2, 3, 4, 5, 6. They are all from the set of natural numbers, right? This F is a mapping. You'll take 1 and map it to 1, right? So just now I have 1. I map it to 1, and then for 2, 2 I map it to 0 here, right? And for 3 I map it to 2, and 4 I map it to -1, and 5 I map it to 3, and 6 I map it to -2, right? So if I move like this, I will cover both sides evenly, right? As I go down the list of the set of natural numbers. Okay, so is that clear to you how to think about doing the mapping? So we have some more practice maybe on maybe next week, right? But this just to give you some illustration, yeah? Okay, so I think I just used up my time, and you might actually have a class at 12, right? So anyway, we will stop here for today, and I'll end the session now, okay? All right, so you can read the rest of the material, and then we will cover that next week, yeah?
Thank you, Doctor.
Okay, thanks for everyone. Thanks everyone for listening. So I'm going to end the recording now.
Thank you, Doctor.